So before we get too many comments popping up, I do want to comment on a consistent issue I was seeing with the discussion board. So there seems to be a misconception about how to derive a rate law from an elementary reaction. So until I start getting questions, let's talk about what a rate law is and where it comes from and how you can kind of diagnose if what you've got written really makes sense. So a rate law, R, describes the rate, so change versus time of how something is changing. And when we have a rate law, there's two components of it. So on the one hand, we have to have our molecules find each other for them to react. And so one side here is the probability they find each other. And the easiest way to figure out this probability is to simply look at concentration. How concentrated is the solution? Now, just because they find each other doesn't mean they react. And so we have to have a second term, which is the probability they react. So the probability they react is going to be represented by our rate constant K. And the probability they find each other is going to be a function of concentrations. So I asked you in the problem statement for the discussion board, what is the rate that the CH3, CH2Br is being consumed in the reaction? And the correct answer is that the rate of CH3, CH2Br is minus K, concentration CH3, CH2Br. So a few things here. First of all, why is it negative? I don't have a negative written here. Well, this R here is just an extent of reaction. So it describes how far the reaction has gone without specifying what it's actually talking about. To scale it to the actual thing we're talking about, we would multiply by the coefficients of what we're interested in. So in this case, there's a 1 in front of here, so multiply it by 1. Now the other reason it's negative is that R is crudely, if it's not in terms of extended reaction, change in concentration over change in time. Well, if the concentration is going down, the change is going to be negative. So this is where the negative comes from. But where does this CH3, CH2Br come from? Well, if we look at the first reaction, it says that for any elementary reaction, the probability that they find each other is just the product of all the concentrations of all the reactants raised to the reaction coefficients. So this is the only reactant, and there's a 1 in front of it, so we would raise it to the first power. So this is how you write any rate law if we're given a reaction. If we want to know the rate of this reaction, it's just K times the concentration of this times the concentration of this. Now, a common mistake I saw on the discussion board was saying that the rate is K, concentration of CH3, CH2 plus, times the concentration of Br minus. And the question is, how do you come to that conclusion? So let's talk about it in terms of a disproof, why that is not a reasonable answer. So let's say I'm running the combustion of something. So let's say I'm burning CH4 and O2. I'm burning methane in the presence of CO2 to form CO2 and H2O. Well, the question I have for you then is, do I need CO2 and H2O to make this reaction go? Because keep in mind, the rate here, the R is describing how quickly the reaction is going. So at the start of the reaction, if this was my rate law, it's CO2 times H2O squared, I don't start with any CO2 or H2O, and so the rate's 0. The change is 0. And this means the reaction would never ever happen. So if my rate law depends on the products, which it can for more exotic rate laws, but not at this level, it would basically say that unless we have a product, we can't start the reaction, which means that since we can't start the reaction, we don't have any products, and you end up with this kind of catch-22 scenario. So your rate law, in terms of a reactant converting to a product, can't depend on the concentration of the products because those products aren't involved in the reaction. It's literally written what's involved in each step of the reaction. Now, instead, let's say this reaction was elementary, the correct rate law would be K, concentration of CH4, concentration of O2 squared. We take each of the reactants, so the CH4 and the O2, and we raise them to the reaction coefficients. So the CH4 has a 1, so we'd raise this to the first power. The O2 has a 2, we'd raise it to the second power. Now again, this is in terms of extent of reaction. If we want to describe the rate of CH4, or better yet, rate of O2, since O2 is a reactant, it would be a negative. There's a 2 in front, so K, 2K, concentration of CH4, concentration of O2 squared. So if this reaction was elementary as written, the rate law, in terms of extent of reaction, which is the easiest one to start with, is K concentration of CH4, concentration of O2 squared. The rate of making consuming CH4, consuming O2, CO2, or H2O, that number in front is going to be dependent on its coefficient. The sign is going to be dependent on if it's a reactant or product. So reactants have a negative change, products have a positive change. So if we want it to do the R, CO2, it would be positive K, CH4, O2. So if you're ever asked to find multiple rate laws, they should all have the same parent term at the very end. K, the probability that the molecules react when they find each other, and the concentration of the reactants that are driving the reaction. Everything else to the left of that K is a reaction coefficient and a plus or minus depending on if it is a reactant or product. So again, this was the most common mistake I've seen. I can tell you that there is very much a question like this on the next exam where it's asked you, given a reaction, find me the rate laws for all the different compounds that are involved. So again, you should not see the products in your rate law. The only exception to this is if you have a reversible reaction. You will see it in much higher division courses when you're deriving rate laws for more complicated reactions, but at this level, unless it's a reversible reaction, the products of the reaction do not show up anywhere in the rate law. I see one person out there today. Are there any questions? Now, another comment I will make, you're going to see homeworks. I said this in a previous live stream, but in case people didn't catch it, you have 2 homework problems, EA from the pre-exponential factor, EA and pre-exponential factors from rate constants, and determining order from concentration versus time data. All that can be found under the lessons course menu under the little test 2 subfolder. There are 2 Excel sheets that you have to download. They are provided to you to find with the raw data for you to process. Now, if you haven't read about how to do graphical analysis or how to find activation barrier using Arrhenius plots, you're not going to know how to do it. Common mistake I see on this homework is that students just plot the data. It is not that type of homework. You're given the raw data and expect to process the data to the point that it can be used to find things like orders, activation energies, and pre-exponential factors. So if you're just plotting the 2 columns of data you're given, you're going to find that you don't get any correct answers. So number 2 in the order of concentration homework. Okay, so let me share my desktop with you. So this is going to follow what's called the method of initial rates. So give me just a minute to transcribe this data to the board. But this is the problem I assume that we're looking at. So we have a rate, a starting concentration of 2 reactants, so 1785, just a minute. So, in order to find the orders of these two compounds, A and B, we're going to use what's called the method of initial rates, or MOIR. Now, with method of initial rates, there's a formula that we can get if we rearrange the rate law. So we're going to assume here the rate law takes the form K, A to the alpha, B to the beta. And manipulating, if we compare two runs, because this is how we would do in the lab, right? If we wanted to know the order of one concentration, we would keep the other concentration constant. So we're going to compare two runs. And to do this, we're going to use the long formula. But if we look at the natural log of the ratio of the rates between two runs, it's going to equal the order of the concentration of A, order on A, ratio of its concentrations between the two runs, plus the order on B, natural log of the ratio of the concentrations of its concentrations between two runs as well. Now, a common misconception I see, and even books will try to promote this idea because they're kind of glossing over a lot of details. A reaction order and apparent order does not have to be an integer. So if we were to derive a rate law, meaning that we were to use, if we knew the reaction mechanism, we were to work it out, everything would have to effectively be an integer. That's because for elementary reactions, there is no way to get a fraction. Now, that said, we don't have a reaction mechanism here. What we have is rate data. We are assuming that our rate law looks like this. Because we are making this assumption, we no longer describe these as orders, and we describe these as what's called apparent order. So an apparent order says that based on the concentration ranges I'm looking at, it looks like the order is some number. Because this is an assumption, there's no theory to back it up, it's purely an assumption, we don't necessarily have to limit ourselves to integers. And you saw that when I brought up the answers. The order is 1.7, the order 1.5. What that would tell you if you got a fractional order is that the rate law really doesn't look like this. It's probably something a lot more complicated. So, that said, how do you use this formula? Well, if you want to figure out the order of A, you need to keep the concentration of B constant. So we would compare run 1 to run 3. So, instead of having a 2, we'd have a 3. We would put in the rate, 0.0633 here, and 0.1785 here. They would equal, this is what we're solving for, the natural log of 0.12 divided by 0.244, plus the order on B times the natural log of these two numbers, but the natural log of 1, so the ln of 0.224 divided by 0.224 here is going to be 0. So if we compare runs 1 and 3, this is what we're left with, and the order is the natural log of R1 for R3 divided by the natural log of the concentration of A for run 1 divided by the concentration of A for run 3. If we want to figure out the order on B, same line of reasoning. If we want to know what B is, we have to change B, but we have to keep A constant, so we would compare run 1 to run 2, and we get that the order of B is the natural log of run 1 for run 2 all over the natural log of the concentration of B from run 1 over the concentration of B for run 2. And you're just going to apply this formula to whatever scenarios you're given. And we could do this with any rate law. Like there's actually a proof for like if you've got multiple things multiplied in there. But basically the takeaway from this is, one, do not assume the order is an integer. It doesn't have to be by method of initial rates. In fact, many times it's not, because very rarely do we end up with a very nice, pretty rate power law relationship when we get done. Now, the other thing about this is that in terms of significant figures, there's no rules. I will specify for these problems how many sig figs to put in there. Traditionally, we would just use 3. But, yeah, I think this would be the big takeaways. But yeah, is that the homework problem you were talking about? I know that was a lot right there. Now, this is also a problem that's going to appear on the next exam. Method of initial rates, graphical analysis, everything you're seeing, the Arrhenius analysis, that's all going to show up on the exam. Oh, you're welcome. I try to keep the problems a bit more simple on the exam, but it's basically this line of reasoning. So, question just got asked: if we choose an oral report topic from the list provided, should we still schedule time to talk with you about the topic? No, that's really what the submission link is more meant for. If you want to pick something off the list, that's fine. I just ask you to talk to me about it just so you don't lose a submission if you choose a project that I don't think, because I have had people pick things that they really were not qualified to talk about. But no, if you want to pick something off the list, just submit the topic. The big thing I need to know is just kind of what you plan on talking about for 10 minutes. In terms of geochemistry, it's more like the chemistry of how like stalactites and stalactites are made. You can get into things like the crystal structure of the different minerals. A biological pump would be more biochemistry, but you can definitely talk about that in terms of like what drives those types of reactions. So if you would rather talk about a biological pump, you're free to talk about it. As long as you can really talk about the chemistry that's involved, that's fine. What I tell all students about these oral presentations, it's important you connect this to chemistry. It's more important you talk about something you're actually interested in, because I had to listen to all these talks. And if you clearly don't care about the topic, I get to listen to you for 10 minutes talk about something you don't care about. So I would rather you pick something that you're passionate about and do your best to connect it to chemistry, rather than pick something that's chemistry heavy that you don't care about at all. You're welcome. Yes, so if you have a 0 out of 100 on the oral report topic, you do need to change your topic. Look at the feedback I gave you. Generally, I think the only topics I've turned down have basically been because so many people have been proposing to do them. I don't want to listen to 20 talks on food preservatives. I've sat through that in one semester, so it's more, the good thing is you've submitted a topic, so you can still submit an oral report. Blackboard has the submission in there now. But again, I kind of want to put some diversity in terms of the presentations that people are giving. So yeah, just resubmit another topic or shoot me an email, and we can talk about what would be a better topic for you to talk about. But I think I've already had like one topic that's been picked by 3 or 4 students. I'm not going to accept any more topics, people giving presentations on that topic. See, I think it's food additives and forensic chemistry, I think the two that are now filled out. You still have, I think, let's see, we have the 4th, today's the 1st. You have until Thursday at midnight to submit your topic. If you have not submitted a topic by Thursday at midnight, you cannot submit your oral report presentation. From 2 weeks from that date is when you're supposed to submit your oral report. There is a reason for that, is that hopefully if you pick it 2 weeks in advance, you've had time to really think about what you want to talk about, and you're not rushing to put the presentation together. If you don't submit, I'm not going to grant you an extension. Like, I don't want you waiting until the last minute to pick a topic, and I don't want you waiting until the last minute to prepare the reports. Because the other complication we have with doing this online, not only, it's not like you're going to show up and give the presentation, you're going to have to record the presentation and send me a link. So there's a lot more planning that goes into the oral presentations for an online course than it does for a seated course where you just show up to lab and give the presentation. So if by Thursday at midnight you have not submitted a topic, you're just going to receive a 0 for your oral report. Because again, I don't want you like waiting to do this. I kind of want to see, like, you need time to write these oral presentations. Other questions? For this exam, a recommendation for you for studying would be to go to those additional practice packets that are under the Test 2 link. They're not, the keys are not explained, but they definitely give you lots of practice and immediate feedback in terms of how to answer the questions. Particularly, I think there's about 2 or 3 pages just on identifying reaction intermediates, identifying catalyst, and there's a whole section on how to do, rate laws given an elementary reaction. So both hypothetical reactions where it's just A plus B goes to C plus D, as well as I think there may be a few in there that are actually like real reactions. So yeah, take a look at those. The next exam that's coming up on kinetics and rate laws, it's one of those that this test becomes more and more the tests become increasingly more bipolar as the semester goes on. This is one of those tests that there's not a lot of room for partial credit. You either wrote the rate law correctly or you didn't. You identified the order correctly or you didn't. There's a little bit of wiggle room in terms of calculations and honest mistakes, but it's really hard to assign partial credit to a problem that asks you to write a rate law and the rate law you have is incorrect. So please do take a look through those additional practice problems. You're going to find the homework, particularly for this test, is substantially harder than the exam. The goal is to walk you through, give you homework that makes you walk through the analysis, but on the exam you don't have to do any data processing. You do have to do data processing for the homework. Alright, so I'll give y'all just a few more minutes, and if there's no more questions, we'll sign off for today. Otherwise, yeah, ask questions, ask away. I'm hoping by this point a lot of you have caught on to the fact that homework is actually pretty representative of the exam. Again, I don't believe in gotcha tests. If you can do the homework, odds are you're going to pass the test. Particularly, I think a lot of you caught that one of those discussion boards was really applicable to that exam. Yes, so in terms of any reactions I give you, they are already balanced for 2 reasons. One, balancing reactions is just kind of a chemistry 1 concept. We're not here to talk about that here. The second is that if you bounce it wrong and then you derive rate law correctly off an incorrectly bounced reaction, that's double jeopardy if I count you wrong. And I don't do double jeopardy on my exams. So for me, it makes life a lot easier if I just go ahead and give you a balanced reaction. So no, you're not expected to be able to balance the reactions on the exam. It's more that given a balanced reaction, can you convert it to a rate law? Or given a reaction and its kinetic data, can you tell me what the orders are? But again, there's no double jeopardy on my exams. If your answer for part A feeds into part B and you get answer A wrong, as long as the work for part B follows correctly, you'll get full marks for part B, even though your answer for A was wrong. The point here is to assess that you know what you're doing. You being given a wrong number is automatically going to give you a wrong answer. But that doesn't mean you didn't understand the concept. It just means that you were giving faulty input. Test 3 actually has to split a week. So when I was trying to figure out what to do, because traditionally what we do for a seated summer course is that you take the exam on one day. So for the last exam, you would have taken it Tuesday last week. So I want to create a range, but the issue is that test, usually the material here is finishing up on like a Monday, and so I can give you the full week. Here the material for test 3 is going to finish up on a Thursday. And so I don't want that whole week to be dedicated to the exam because you're not going to be through the material by Thursday, which only gives you Thursday or Friday to take the exam. But I also don't want to start the exam the following week because you basically will finish the material and not, like, you won't be able to take the exam. So test 3 actually straddles 2 weeks, and unlike the other exams you're going to see where you basically get 4 days, you're going to get a full week for this one. I'm going to give you additional weekend time. So test 3 actually straddles 2 weeks. It's not during one full week. It looks like it's for 2 weeks, but it's really not. It actually just kind of like starts on like a Thursday and finishes on the following Thursday. Or starts on a Wednesday and finishes on the following Wednesday. The other point was just to kind of give you a gap between the second and third exam. Otherwise, you would have taken the second exam, and then the way it worked out, you would immediately turn around and taken the third exam. Or it would have been like you would have taken the third exam and immediately taken the fourth. It's kind of meant to break up the testing windows. Other questions? Test 3 will also, sure, the final is going to be the hardest exam you take. The final is hard just because it's cumulative and there's just a lot of different topics on it. Test 3 is just hard in the sense that the material is hard. It's meant to kind of be, it's two separate concepts that we had to cover separately and then blend back together, and that's just what makes it hard. Is you have to keep learn two separate ideas that eventually feed into each other. But again, I'm going to try to provide you with a lot of practice resources for this, particularly with the thermodynamics. There are a lot of practice problems that'll be at your disposal. But again, that's like towards test 3. Other questions? One more example with multiple steps. Example of what? So example of deriving a rate law, or an example of like finding orders? Reaction rate. Okay. So typically when we talk about reaction rates, the Blackboard discussion board was far more complicated than we normally talk about, but that was meant to test multiple concepts at once. But let's say we had the reaction C3, H7, now we'll make it easy, H8O, it's a liquid, plus H plus, goes to C3, H8, OH plus, C3, H8, C3, H8, OH plus decomposes into C3, H8 plus, think about this reaction before you. Oh, yep, you lose 2. It's H2O. And then C3H7 plus decomposes into C3H6 plus H plus. So, if this is our reaction and I ask you what's the rate of C3H8O consumption? Well, we're going to assume that each reaction here is written elementary. And so the rate law, the general rate law, R, can be written as K, the rate constant, times the concentration of each of the reactions. So C3H8O, concentration of H plus. Since each of these have a hidden 1 in front of them, we're going to raise them to the first power. To convert this to C3H8O, what we need to ask ourselves is, 1, is it a reaction or product? So since it's a reaction up here, it's going to have a negative change. Now, the next question we have to ask is, what's the coefficient in front of it? So there's a 1 in front of it, so it's going to be 1 times K C3H8O concentration of H plus. So that would be the rate law for finding the rate of K of C3H8O based on this reaction. Now, more likely, just to kind of simplify, make sure you're understanding the concept better, what you would more expect to see for a type of question like this is, let's say the reaction C2H2 plus 2H2 going to C2H6 is elementary as written. And I ask you, what's the rate of C2H2, rate of H2, and the rate of C2H6? The easiest way to do this is just to write out your generic rate law. So R here is K, concentration of C2H2, concentration of H2 squared. So the rate is the rate constant times the concentration of each reactant raised to its reaction coefficient. Now, to figure out C2H2, H2, and C2H6, first, are they reactants? These two are, so their changes are negative. This one's positive because it is a product. Next, what are the coefficients? So the C2H2 has a 1, the H2 has a 2, and the C2H6 has a 1. Everything to the right is just this parent rate law. So 1 times K, C2H2, H2 squared, K, C2H2, H2 squared, K, C2H2, H2 squared. So all of these have that parent rate law in them with a sign and a scaling to represent basically what they actually are. Now, the way to rationalize this, if we have 1 mole of C2H2 consumed, that means we have 2 moles of H2 consumed at the same time. So that makes sense then to say that the rate of H2 consumption is twice as fast as the rate of C2H2 consumption because it takes twice as many moles. It also makes sense to say that because these are 1 to 1, we'd expect this to be consumed at the same rate that this is produced. Now, in terms of orders, this is first order with respect to C2H2. This is second order with respect to H2, and overall it's a third order reaction. All right, so I've also got a request for number 6 in the Kinetic Models homework. So I'll share my desktop with you really quick. So the question asks, if you have titanium plus 2 consumed by second order kinetics, what is the concentration of Ti plus 2 after 1.68 seconds? If the starting concentration is 7.33 molar, and the rate constant K is 0.480, 1 over molarity times seconds. So to solve these types of problems, there are 3 kinetic models. Zero order, which says that the concentration of A is its starting concentration minus KT. First order, concentration of A is equal to the starting concentration times E to the minus KT. And then for second order, there's 2 forms. The most useful form is 1 over the concentration minus 1 over the starting concentration equals KT. So this is a second order reaction according to the problem statement, so this is the model we're going to work with. What we want to know is the final concentration of Ti plus 2. So 1 over the final concentration minus 1 over the starting concentration, which is 7.33, equals the rate constant K, 0.480, times the time, 1.68. And all you have to do here is just rearrange for algebra. So the concentration of Ti plus 2 is 0.480 times 1.68 plus 1 over 7.33, 1 over the whole thing. And that will give you the concentration of titanium plus 2 at the time given. In terms of assuming elementary, for the test, I will explicitly say if the reaction is elementary or not, but do not assume it's elementary if you are not told it's elementary. Most reactions are not elementary as written, and that's a bad assumption to make. So again, unless I explicitly tell you this is an elementary reaction, do not make that assumption. Yeah, you're welcome. Other questions? Yes, if your lab kit doesn't show up, let me know. Apparently, Carolina Biological made promises they couldn't actually keep. So we're being very understanding if your lab kits don't show up. Mine still has not shown up a month later. Also, please let me know if it does not show up with vinegar and hydrogen peroxide. We found out Carolina Biological couldn't get a hold of any, so they're just shipping the kits out without them, with the assumption that you're going to get a hold of it. So yeah, I'm being very flexible with extensions for the labs right now. If your kit doesn't show up, send me an email. I'll just keep giving you week extensions until the kits show up. They promised June 1st to a lot of students. We'll see if that materializes or not. If I don't immediately grant you the extension, don't think that I'm not going to give it to you. I'm probably going to wait till Thursday and just do all the extensions at once. So yeah, if you've emailed me and said, hey, I don't have a lab kit and extension, I'm going to give it to you. Just, you're not going to see it in Web Advisor till about Thursday. But yeah, I'm not going to hold you accountable for a kit you don't have. Like that's just cruel and unusual. And as faculty, we are actually discussing this in the background. We're worried. Again, Carolina Biological promised us. We told them how many students we were expecting to have. They said they could totally meet that demand. And now I got one instructor who says that 2/3 of our students don't even have kits. They're all back ordered. Fortunately, most of y'all got your kits, so about half of you were able to get the kits in on time. But we might also talk about doing alternative labs. It's a bit of a sticky situation with the alternative labs because you would need the lab manual. So you would actually need the C lab manual, and those labs are very different than what your kits would do. So we're still kind of working it out. But for now, I'm just basically granting extensions. And if we get through halfway through the semester and I'm still granting extensions, you're still going to get them. Or if you still need extensions, you're still going to get them. Other questions? Give you a few more minutes, and then if no one's got any more questions, we'll sign off. So I'm going to work a problem just because it's bugging my curiosity, but you don't need to know how to work these types of problems. So we talked about this example earlier. Again, you don't have to worry about being able to do this type of analysis. I'm just trying to satisfy my own curiosity. So if you want to write the rate law for the consumption of C3H8 and H+, that's easy. But let's say you want to describe the rate of C3H6. Well, that's minus K. I'm going to put 3 because this is the third reaction. Concentration of C3H7+. The thing is, C3H7+ is not something we put in the reactor. So the rate, C3H7+. So, pseudo-studies, state approximation. Drop that in there. Okay. Satisfied my curiosity. All right, so into the live stream tomorrow, Wednesday and Thursday. Please email me any questions you have. Keep in contact via email and via Teams. If you're not going to be able to make it to the live streams, come about Teams, and it's just more of a practical thing. Send me a chat through Teams. Don't respond to the course website or the Teams. Don't comment within the team itself. Big reason, Teams sends me alerts saying that people have commented, but it doesn't tell me what team they're actually in. So I have about 30 teams I'm part of. So if you put a comment in, there's a good chance, particularly now that we're all discussing the different issues we're having with Carolina Biological, that I'm not going to see it if you comment in the course. But if you do a chat, it actually gives me a specific link to that chat. So if you need to ask me questions in Teams, do it directly through the chat feature. Don't do it through our group team. Other than that, I will see some of you all tomorrow. All right, thanks for showing up.